Welcome to today's lecture on areas for section 6.2 and Riemann sums from section 6.3. We'll start by going over section 6.2 on the definite integral as the net change of a function. And then we'll talk about the definite integral as the area under the curve and how both of these relate to the fundamental theorem of calculus. Here's how we define the definite integral. If capital F of x is an antiderivative of little f of x, any antiderivative, then capital F prime of x is little f of x. The integral from a to b of f of x means the net change of f. The integral from a to b of f of x dx, this is a new symbol. It means the definite integral. We saw before a symbol for the indefinite integral or antiderivative, and this definite integral is equal to the net change f of b minus f of a, that is the net change of the antiderivative of the function that is written right before this dx. In this notation, this function here is called the integrand. F of x is called the integrand. The above equation is called the fundamental theorem of calculus. And any antiderivative, capital F of x, will give the same value for the net change. F of b, capital F of b minus capital F of a. It's an important difference here. This definite integral is a number, while the indefinite integral, or antiderivative, f of x dx, is a family of functions. Remember we saw before a bunch of formulas for the antiderivative or indefinite integral that looked like a function plus a constant. That's a family of functions because all those work. But here, if you feed this definite integral, if you put a function in the integrand and are asked to compute integral from a to b, the lower limit and the upper limit of the f of x dx, what you're going to get is a number, not a function. Now, the rules for the definite integrals, they pretty much inherit the same rules as for the indefinite integral. So if you have two functions and a constant, the sum of the definite integral of a sum is the sum of the definite integrals. The definite integral of a difference is the difference of the definite integrals. And you can call it a constant. The definite integral of a constant times a function is a constant times the definite integral of a function. Here's an example. Find the net change in position when velocity is given. A rock is dropped from a building whose height is unknown. T seconds after the rock is dropped, its velocity is negative 32 t, and its height is h of t, some unknown function. So I'll draw a little picture of what's going on here. We have a building, we have a rock, and it's dropped. We know its velocity, minus 32t, and this actually is from acceleration due to gravity, but its height is unknown because the height of the building is unknown. What is the net change of the height of the rock between t equal to 1 and t equal to 2? That is, what's h of 2 minus h of 1? Remember, h is an unknown function, but we can still compute this net change, h of 2 minus h of 1, using the definite integral. How do we do that? Well, we put at the definite integral from 1 to 2 of the velocity, v of t, and we compute. Now, there should have been a dt here. Definite integral of from 1 to 2 v of t equals definite integral from 1 to 2. We just plug in negative 32t into here. And what do we get? We get h of 2 minus h of 1, and that gives the net change in height, right? The height of the rock after 2 seconds minus the height of the rock after 1 second. How do we compute this? We use the rules for definite integrals we saw above. Take out minus 32, And recall from before, right? What's the antiderivative of t, or t to the first power? It's t squared over 2. T squared over 2 plus a constant. So there should have been plus c here too. But we can use any constant, so let's make it simple and just choose c to be equal to 0. That's going to make calculation simple. We get an antiderivative of t, right? T squared over 2, its derivative is t. So the definite integral from 1 to 2 of t dt is capital F of 2 minus capital F of 1. That's 2 squared over 2 minus 1 squared over 2, which is 4, over 2 minus 1 over 2, which is 3 halves. H of 2 minus h of 1 is therefore minus 32 times the definite integral from 1 to 2 of t dt. We found that this value is equal to 3 halves, so we get negative 32 times 3 halves. Minus 32 over 2 is 16. 3 times 16 minus 3 times 16 is negative 48. So what this means is that whatever happened to the rock, however high the building was, its net change from t equals 1 to t equal to 2 was 48 feet. And notice it's negative because the rock is falling, so its height after 2 seconds is going to be smaller than its height after 1 second. A smaller number minus a larger number is, of course, negative. Let's summarize what we did. What are the steps in the previous example for computing a definite integral? To compute, let's just spell that E should not have been there. It just should have been C-O-M-P-U-T. To compute integral from a to b of f of x dx, we follow these steps. First, find any antiderivative of the integrand. Next, evaluate the antiderivative at the upper bound and at the lower bound. Step 3, compute the difference. The definite integral as an area. Function that is not negative on a to b. So this is the second interpretation of the definite integral as an area. We have some function that is not, it could be any function, that is not 0 on an interval. So this is what if it was graphed in axes, it would look something like this. It always lives above the x-axis. And the definite integral, it turns out, computes the area under the curve, y is equal to f of x, from x equal to a to x equal to b. So what's going on here, this is a, this is b. The definite integral is computing this area here. This upper curve is the function fx. Here's the first example. This is pretty simple. If we have a positive constant, our function is some constant. This should have said the definite integral from a to b of f of x dx is c times b minus a. In that case, what does this look like? Well, this looks like just a horizontal line. The graph of constant, of course, is a horizontal line. And if you look at the area under a horizontal line, from a to b, you just get that shape. What is that shape? That's just a rectangle whose width is b minus a, whose height is c. Height times width, c times b minus a, gives you the area. Second example is to compute 0 to 2 of 3x dx. Now we could compute this by using the antiderivative method outlined above, but we're going to do this by interpreting it, the definite integral, as the area under a curve. And here's the next slide where we do this. We visualize it. Here's the graph of y is equal to 3x. It's a line, and if we look at the area under the curve, if we draw the vertical lines x equal to 0 and x equal to 2, what does that cut off? That bounds, so that creates the shape of a triangle. Its base is 2 and its height is 6. So the area of a triangle, if you recall, is the base times height divided by 2. 6 times 2 is 12, divided by 2 is 6. So we conclude the area under the curve y is equal to 3x from x equal to 0 to x equal to 2 is 6. Or equivalently, the definite integral from 0 to 2 of 3x dx is equal to positive 6. So now that we have that down, let's talk about Riemann sums. Now, Riemann sums are about approximating the area under a curve. Again, we start with the non-negative function, a function that's never negative on an interval. Remember, the definite integral from a to b of this function, half of x, is an area, computes an area. Therefore, it can be approximated by areas of rectangles as follows. We divide the interval from a to b into subintervals of equal width. So this is a to b. We divide it up. 1, 2, 3, 4, 5 division lines. 1, 2, 3, 4. There would have been. One, 2, 3. So you can see there are 4 subintervals. 1, 2, 3, 4. And that would have been an example where n was equal to 4. You divide this into n subintervals of equal width. The equal width is b minus a over n, and it forms the width of a rectangle that's going to be constructed over it. So if you look at this interval from a to b on the number line, and we have this subinterval, we're going to construct a rectangle above it. And that rectangle is going to approximate the area under a curve. We're going to select a value, xj star, in that interval. And then what we're going to do is we're going to construct we're going to evaluate the function at that value in this subinterval. Half of xj forms the height of the rectangle that's constructed over the subinterval. So if this was our subinterval, we have a rectangle that's constructed over it, and its height is given by f of xj. F of xj star. If we add up now this, how many subintervals do we have? There's n subintervals, so we have n rectangles. We add them all up, f of x, and because this forms the height of the rectangle over the subinterval, it has area height times width, which is f of xj star times delta x. We add up the in rectangles, so because they're in subintervals, they're in rectangles, and we get the Riemann sum, f of x1 star delta x plus f of x2 star delta x, all the way up to f of xn star delta x. Factor out the delta x, we're left with this. This approximates the integral from a to b of f of x dx. Left endpoint, right endpoint, and midpoint, Riemann sums. If xj star is just xj, we get a right endpoint sum. Remember, the subinterval was x sub j minus 1 to xj. Right endpoint is xj. We have this right endpoint sum, which is f of x1 plus f of x2 all the way to f of xn. Multiply that by delta x. If xj star is xj minus 1, the Riemann sum is a left endpoint sum. F of x naught plus f of x, this should have been f of x1, all the way up to f of x n minus 1, times delta x, the width of each subinterval. If we choose xj star to be the midpoint, the number that's exactly between xj and xj minus 1, xj plus xj minus 1 over 2, the Riemann sum is a midpoint sum. And n, f of x1 star plus f of x2 star plus f of xn star. Notice that in all these formulas, this delta x remains the same. This is always the same. What's changing is xj star. It's either one of the two endpoints or it is the midpoint. Let's summarize what we've learned. We learned what a definite integral is and its two interpretations, as a net change and also as an area. If we choose larger and larger subdivisions, let's draw a picture of what's going on here. So we have some function and we're approximating it, the area under this curve, by using rectangles. You see each of these rectangles here, right? From A to B, these three rectangles approximate the area under the curve. And if you keep using finer and finer divisions, so that last picture there were three rectangles. If I draw another picture now, it's going to be more accurate, right, if there's more rectangles. Let's say we draw 1, 2, it wasn't quite right. You should get the idea. 3, 4, now there's 5 rectangles. That's more accurate, as you can see. This is more accurate to the area under the curve, y is equal to f of x from A to B, than just those 3 rectangles. If you keep choosing larger and larger subdivisions and add up those areas, you're going to get an area that's closer and closer to the actual area under the curve. Delta x, of course, if n goes to infinity, any constant, in this case b minus a, the length of the interval, divided by n goes to 0. And f of x1 star, this should have been a superscript, but f of x1 star plus f of x2 star, doesn't matter which values we choose in each subinterval, this approaches the definite integral from a to b of f of x dx. Here's the fundamental theorem of calculus. Revisited once again. If we have n antiderivative is equal to f of x, and the limit as n goes to infinity of this sum, this Riemann sum, is equal to the integral from a to b of f of x dx. That's equal to the net change of the function. So here, left-hand side, this is interpreted as an area under the curve from a to b of f of x. And here, this is a net change. Now, we've only really talked about areas for cases where f of x is a positive function, but you can also define this value, right? F of x1 star plus f of x2 star plus f of xn star times delta x, where delta x is b minus a over n, when f(x) is a continuous function that's allowed to be negative. Okay, so that's it for the lecture. Best wishes. Uh, I will be uploading probably a classwork for this weekend, either Saturday or Sunday, and I'll definitely be getting a practice exam up by Monday.